And so that's all for sampling distribution. What about from the exercises? What about the quizzes? How many people didn't get this far? You should be completed, your attempt at this, so I can start inference. But we can take some time, like I said, to talk about this. No comments? All right, this is where I'm going to start. I'm going to start with, let's talk about the formula sheet. That will be my review. And make sure your formula sheet is the same. Okay, so this formula sheet. So I spend the rest of the videos, I refer to this formula sheet and I elaborate on it because this summarizes, this is like your outline, summarizing the rest of the course. So I focus here. In the first part, we have a summary of binomial and what you learned there. Now, I did a lot of proofs, and it's fine if you don't understand the proofs or you don't follow. It's okay. I'm never going to ask you about them, but it provides the foundation for what we do here, right? And we learn that, and we derive the formula using rule for independence. We derive this pattern for the binomial distribution. And this is, we spent some time on this last class, so this shouldn't be so bad. Just remember that what we're doing is multiplying the number of successes, the probability times the probability of success times the probability of success, multiplied by the probability of failure by the number of times that there are failures. So that's success, that's failures, and then this is the different number of arrangements for seeing that pattern of case successes. And then I went a little over to say, well, this is a discrete distribution, but in specific cases, you can find that the pattern of the distribution is symmetric, and even further, it could be approximately normal. Now, this you can understand before computers was very useful for statisticians to just rely or fall back on the normal distribution, which they had tables for. And although the approximation to the normal distribution of the binomial was not exact, I did show you a way to get an exact value using the continuity correction. So to know that a distribution that's binomial is approximately normal, you have to verify that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. And the other way to know, so it's a combination of the p, which we notice if the p is 0.5, we know it's going to be symmetric, but it might not necessarily be normal. The higher sample size will make it, even if you don't have a p of exactly 0.5, higher sample size will make it closer to normal. So this combination turns out to make the distribution look approximately normal, and then we can use the normal approximation to estimate the value of the probability. And that's all we're doing. We're finding distributions and solving for their probabilities. That's what we spent weeks doing now. And it turns out also that for that normal distribution, we can find the mean of the binomial as n times p and the standard deviation as n times p times 1 minus p square root. And I proved it. And if you don't understand that proof, just remember where you have to look to get those numbers, okay? All right, so from there, I start talking about the reality, of using this distribution the number of successes, like the number of people who support Donald Trump, or the number of people who got COVID last week, or the number of people. So you're looking at the number of people. This is a count variable. We're counting. So we call this like a count variable. And we use the symbol X. Now, we've used X before for normal, and we've talked about X, but now I'm going to use it by specifying that it has parameters N and P. And the reason they are parameters is because knowing those is all I need to know. I need to know I have a binomial distribution N and P, and I know all the probabilities of the different possible values of X. So from there, I convert that into a proportion because the sample proportion is more common to be, like, more commonly we speak about the sample proportion, which is just derived by taking that X and dividing by N. And the sample proportion, like the proportion of people who favor Trump, the proportion of people in a city who contracted COVID, the proportion. So that's more like what we hear, right? Not just numbers, you hear proportion. So we translate what we found up here into the sample proportion by dividing by N. And it's just as easy because of our rules of means and variances. All we have to do is divide. If we divide X by N, which is now a new variable. Well, let me see if we create this new variable X hat, X divided by N. Oh, you guys are not seeing I screwed up. I got to show you my iPad. Hold on. I've been writing notes. Okay, there you go. So I just made some notes there. You can copy. All right, so I call X the count variable, and I call a P hat dividing by N the new variable called the sample proportion. And just because of the rules of means and variances, all I have to do to get the new mean is to take this one and divide it by N, and I get P, which feels weird, but it makes sense when you think about it. On average, that's what the mean is, right? On average, we expect the sample proportion to be the true proportion. So that does make sense, you know? And then we would divide this by N, and it gives us, we like this form of the division. So to get that, we take square root NP1 minus P divided by N. Now, how do we do that? To put N inside of here to simplify, like we could leave it like this, we could, but the form of the calculation that we use is this one, where I put the N inside, and then I cancel this one with one of those, and that's where that formula comes from. All right, so all I did was divide by N, and it's because it's more practical. And you'll see, even though I've spent a lot of time talking about X, the count variable, the number of successes in N trials, I move to the proportion, and then we kind of stay there. All right, we stay with the proportion. Same rule applies about X being approximately normal. And then this carries to the sample proportion. Also, in repeated samples, we find that this also has a approximately normal distribution. And then from there, we actually derive sampling theory. All right, so what you learned, so this is part of what I called BIN, binomial, but it also, this part here is touching on sampling distribution of a statistic. So because it's the sampling distribution of X has a mean and a standard deviation. So they're in here are both BIN and SDS. And then here, this is really about SDS, the sampling distribution of the statistic called the sample proportion. So I've called it a variable, but it's a statistic as well, isn't it? Why is it statistic? Why can I call it a statistic? Because this means sampling, distribution of a statistic. Why is it a statistic? So X is a statistic. P hat is a statistic. Go back to understanding what is the definition of statistic. It's a number computed from a sample. Isn't that computed from a sample? We're counting out of a sample of N, how many are successful. This is a statistic. Out of a sample of N, what's the proportion that are successful? So it's a variable, it's also statistic, and that's what we're working on. We're finding a distribution of a statistic. Okay. So this statistic is a variable and it has a distribution. And yeah. Then there's also another statistic, and that is if we're interested in the mean. So the mean, we already know mean is like average height, average weight, average income, or average grade. Okay, so that would be, so problems that deal with averages, you look here. Again, this is going to be sampling a distribution of a statistic, and the statistic is X bar. We know what X bar is. So we've gone from X to P hat. And then we have X bar. And X bar, let me write one more thing. I'm going to write P hat is distributed normal with a mean of P and a standard deviation of P 1 minus P over N square root. So each time I can derive this distribution. That's what that's saying here. This is what this is all about here. And this one, we learn about X bar. X bar, if we know about X, where X has a mean of mu and a standard deviation of sigma, what do we know about X bar? So in other words, if we're talking about average grade, then what if we take the grade of one class, one semester, and we take the average grade of another class, another semester, and we take another average of another, another class in a different semester. So we have all these different averages. What do we know about the distribution of all those averages? Well, the theory says if we know the mean of the distribution of X, so all grades, I'm making this really broad, but all grades of MBA students in this course, and this is known. Say we knew it, say we observed it for a long time, and we know the mean and standard deviation, then we know something about the sample mean. That is the average of all those different samples, the means of all those different samples. We know that it'll have the same mean, but the standard deviation, because we're just looking at a distribution of means, those means are closer together. Okay, they're more common, or they're more narrow than the overall values themselves. And so that is captured here. And actually, mathematically, it turns out to have, because of the way we derive X, the distribution that is normal with a mean of mu and sigma, we can find that the standard deviation of X bar is smaller than sigma by exactly this factor, by dividing by square root of n. So this is true when is this true? So I've written this down now, but when is this true?
When n is big enough?
Not necessarily. If you know that X, let me write it. If X is normal mu sigma, then X bar is normal mu sigma over root n. So if you're given this, it will be true. If you're not given this, now you can speak. Who just told me that answer?
Carolina.
Carolina, okay. So Carolina, you're correct if you don't have this information. It's only true if you have a large enough sample. And often it's the case that X bar is approximately distributed. We don't say it's exactly, we say it's approximately distributed normal with the same mean and a smaller standard deviation if n is greater than or equal to, do I say 30 or 25? I don't know why I'm judging. Sometimes, did I say 30?
I think it's 25.
Oh, I use 25? Okay, I don't know why. Sometimes textbooks use higher, but 25 is easier for the math. So, and you take the square root, you know, it's 5. Okay, so X bar is approximately normal mu sigma over root m if n is greater than or equal to 25, when we don't know the distribution of X. So I've used X several times. I went from using X as a binomial to down here, I'm using X as a normal. So as a normal, okay, so you have to always look back and go, okay, what was the distribution of X? Because just saying X is not going to tell you anything. You need to know what it means. Okay, so this last thing I said is the more realistic. It's unlikely that you're going to know the distribution of X. And so usually samples and studies are done with samples larger than 25 to be sure that what they're getting is really meaningful, right? Out of their samples. So that's what this says here. X bar is normally distributed, provided X is normally distributed and approximately normally distributed if n is greater than, oh, there it is, 20. Okay, so that, so let's look at those problems that I've been given, number 3 and 4, and we'll talk about this. This thing here, this rule is known as the central limit theorem. It has a special name. This is known as the central limit theorem, and that's what we're going to apply. And so that you can get the same result as long as your sample size is big enough if you don't know anything about X's distribution. All right, so let's look at those problems on page 41, and then let's see what else I can add. And then I can just continue down my formula sheet to talk about inference. Oh, my numbering is different here. Okay, So let's work off of here. I'm going to take this away. Okay, so so from now on, you're going to refer to that formula sheet. Everything you need, most things you need are going to be there. You just need to know how to use it. Suppose that the moisture content per pound of a dehydrated protein concentrate is normally distributed with a mean of 3.5 and standard deviation of 0.6. A random sample of 36 specimens, each consists of 1 pound of this concentrate. Wait, I read that weird. A random sample of 36 specimens, each consisting of 1 pound of this concentrate, is to be tested. I think it's just this typo here. So this is N. Now, X bar denotes the sample mean of these measurements of moisture content. So what do we know? We don't have information except that X is given as with a mean 3.5 and a standard deviation of 0.6. Oh, they're told it's normal. Sorry, I'm wrong. I did that wrong. Do that again. So we need this as well. So it's normal with a mean of 3.5 and a standard deviation of 0.6. And because of that, with N equals 36, which we don't need it to be large because it's already known to be normal. We know the shape. So then X bar is also normal with the same mean, but a smaller standard deviation. So it's 0.6 divided by, so it's relative to how large your sample size is. So in other words, if you want those averages to be closer together so that your estimate is more precise, then you take a larger sample. So this is 0.6 divided by 6, or in other words, 0.1. Okay, so I've just derived all that information. Let's see what we can answer. For A, what is the distribution of X bar? So what is the distribution? What is the answer? Did I already write it?
Yeah, it's normal.
It's right here, right? So this is it. So you write, so X bar is, well, you can express this whole thing as evidence. So this would be the answer to this. So X bar, it means that this is true and it is exact. And also for B part, I got the mean and variance for the B part. So you're going to say, so I sometimes I write with this notation, the mean of X bar is 3.5 and the standard deviation of X bar is 0.1. Just to denote it distinguish it from X. Now we have a distribution that we can use. So we can answer the next question, C, what is the probability that X bar exceeds 3.7? So you just have to do one step and then you end up with the normal distribution, the standard normal that you know how to use, right? Because you're not allowed to forget anything you learn in this class. So you learned that before, we got to use it. So what do I do with this? I standardize it. I turn X bar into a Z, and 3.7 minus 3.5 divided by, what do I divide by?
5.1.
Very good. So now you look here because that's X bar. So that's your distribution. You don't look at the old one. and simplify.
That would be 2.
Yeah, 2.
Yeah. And we have an idea of what that's going to be because we've done problems like that with 2 before, right? We know that between 2 is 95% and that leaves 5. So this is like around 2.5, but we should look it up on our table. Draw a picture, don't forget. I want to be at 2 and greater than 2 for the Z. One thing I can do, there's 2 ways I can do this. I can look up 2, which will give me the left side, but I want the right side. If I look up 2, I get this number here.
0.9772.
Mm-hmm. Right. So I will get 0. Oops, it's not going to be there. That's what I want, but it's going to give me this, right? Because the table only gives me the left side. And so I have to take 1 minus 0.9772, which is 0.0.
228.
228.
Right. And like I said, it was going to be about 2.5, right? Because 5 would have been the outside, and then half of 5 is like 2.5. So that's just roughly, those are approximates. If you're using the 68, 95, 99.7% rule, it's just an approximate. But here we're getting more precise. So so that's the answer. The other way to use the tables at this point, you should be comfortable, or you can follow when I say, because of the symmetry, it will be the same answer on -2 as it is on 2, right? And I'll get the answer right away. If you change the sign and the direction, you have the same answer. And that's because of the symmetry. So if you look this up on the table right away, you will get exactly. So I gave you some time between when we learned this and now, and you should be comfortable doing that. If I flip to the other side, you have to change direction. So the arrow goes this way and the sign changes. All right. And we're done with C. That's C. And D. You guys want to try D without me? Try D. And then we'll talk about E. So I'll give you 5 minutes for. Okay, should I try? Oh, I'll give you a few more minutes. I'm rushing.
Professor, I need to disconnect myself because I have some issues with my internet. I will come back in a few minutes.
Sure. Okay, ready? So between. So I know that means I have to put X bar. Don't forget we're working with X bar. Between always means the arrows go small to big, small to big. And put 3.4 and 3.7. And I'm going to do the same thing I did above. (3.4) minus the new mean, 3.5 divided by 0.1, and this turns into a z. Minus 3.5 divided by 0.1. I'm starting to lose my voice. So you have -1 and
2.
2. Draw a picture. And we want the area between, but to get it, we're going to extract this lower than -1 off of 2. 2 we know, we have that from up here. No, we don't. We have up here. So I know that's 0.9772. And less than 1, -1 is easy. You know that one?
0.587.
Yeah, so you should get used to some of these numbers. They repeat. 0.1587. And between, don't forget you can also use Excel for this. Just have to remember how to use it. And what you're getting, right? Because it also just gives you the left side. Excel gives you the left side. And we have the answer.
0.8185.
That's right. Okay. So it's repeating what we learned about the normal distribution, but we have to create our normal distribution from the rule of the sampling distribution of X bar. Now I'm curious what I got for E. What did I say here for E? So all the answers are here. So if I don't think I asked that question well. What are the approximate values of X bar and its standard deviation? It will follow a normal distribution with the same mean, but because the standard deviation depends on n, this number changes, right? Because it's dependent on n. That's why that's the idea of it being a sampling distribution. Changes with the sample size, because this is always sigma over root n, where sigma was given as 0.6, but this changes depending on what your sample size is. So 0.6 divided by square root 5,000 gives you that number. Questions? So once we standardize, everything falls back to the standard normal distribution. Oh, I haven't looked at the chat at all. Sorry. Great. Thank you. Thank you for your participation. Okay, so then the other question was about 4. Question 4. So what's different about 4 and 3 than 3? What is new? What is the different thing? Why can't I do it like I did it before?
I don't have the type of distribution.
Right. Now you can proceed if you make an assumption, but otherwise you don't know anything. The age of women, unless your sample size is large enough, those are the steps of thinking, of logic. If I don't know the original distribution, I have to have a large enough sample size. The age of women with a certain disease is 42 years on average, with a standard deviation of 2. What is the probability that a woman with a disease is over 40 years of age? So what do I do here? So let's write it in symbols. So we're talking about the same thing, right? So X is, we don't know the distribution, but it has a mean of 42 and a standard deviation of 2 in age. What is the probability that a woman with the disease is over 40 years of age? So basically, you can't do this unless you know the distribution of X. We learned about a few different distributions. If you don't know the distribution, well, you can't do anything, right? So we'll assume it's normal. So we assume that X is normal with a mean of 42 and a standard deviation of 2. And now we can answer it. How do we answer it? We use just the normal distribution like we usually do. (40 minus 42 is -2 divided by 2 is -1. And notice we're going greater, so don't make a mistake to go the wrong way.
It will be 84.
0.84.
8413.
Yeah. As you draw a picture and you know you're here and you want to go this way. So when you look it up, you look up -1. And when you look up -1, you get 0.1587. So you do 1 minus, or you can just look up less than +1, change the sign and direction, you'll get the same answer. Sign and direction. Okay. And now I'll let you think about the next one without solving it. Think about what is the dilemma there. So in a sample of 100 women with the disease, what is the approximate probability that a woman with the disease is over 40 years of age? So now I'm looking at the sample. Mhm. So I used just some, I wrote things out in words. So I said X is the age of a woman with a certain disease, right? So I said X equals age of woman a certain disease. And then I define, so then I say, okay, X is 42, 2. And then I say X bar is approximately normal with a mean of 42 and a standard deviation of 2 over square root of n goes there. But I'm going to have 100 women, so it's going to be 0.2. So what we're using here is called the central limit theorem, the central limit theorem. I use the central limit theorem to do this, or I can just do what I did above and assume that X is normal, then I don't have to use it. That's all I'm trying to emphasize. It's either you make the assumption that it's normal and then you don't get an approximation, but you're assuming, or you just use the central limit theorem.
Professor, I have a question.
Yeah.
Why we assume that it's point two?
I did not assume what I did was I'm looking at the sample of the women now. So I feel like there's a word missing here that maybe is confusing, but this is the age of a woman. And
Mhm.
this would be the average age of a woman in the sample. So I think I said that here.
N is missing.
Oh, I didn't write N? Oh, 100.
Mm.
Yeah, no, I did N. N is here. Here. It's 100. And
Mhm.
square root of 100 is 10. I skipped a step, I guess. Does that answer the question?
I think so.
No,
I-
that's-
I understand the difference between assuming it is normal and invoking the theorem. Like, what's the difference in like writing?
So here, I assume to do anything, I had to assume X is normal or I can't do anything. Here, I don't have to assume X is normal to talk about the sample mean. I can just use the central limit theorem. That's the point I'm making. So here you don't have any escape. You have to assume normality. But the central limit theorem gives you the power. If you have a sample size large enough, you don't have to assume normality over here. So I think that's the difference that I'm trying to stress here. Should I write it down? I think I did in the solutions. Let me see what I wrote. Let's see, so I don't contradict myself. So what did I say here? We assume X is normally distributed so that we can solve this. Oh, what did I do here? Oh no, that's the B part. Sorry, I missed the A part. We have no choice. We must assume X is normally distributed or we can't answer this. We could just, like, we have to assume it to get an answer. We're forced. Otherwise, we're just staring at this and with nothing to do. In the B part, though, we can assume X is normally distributed like we did before. And then automatically X bar is also normally distributed. Or we don't have to assume X is distributed. We can just use the central limit theorem and say X bar is approximately normal with this result. So it's the same result. And the issue is whether you're getting it exact or as approximation. But to get it exact, you have to assume normally distributed here. I'm separating between this outcome and this outcome, what it takes. This has less assumptions, right? Now, this won't work unless your sample size is big enough so that you have to spend some money to get a large enough sample size. There's always a cost to pay, trade-off. So no assumption necessary here. That's the beauty of it. Now, the answer ends up being essentially the same. And that works out. The answer is the same in A and B, or sorry, in either alternative, because N was bigger than 25. We were able to do that.
So, Professor, to be clear, when we assume, we are assuming we have the PERC, but we have a exact result. And when we use the theorem, we are not assuming, and we have an approximate result.
Yeah, so we lose something. and that the result is approximate. But in getting the approximate result, we didn't have to assume something that we have no proof of. Okay, but yeah, so this would be exact, but with a assumption that could be wrong. And this way, using the central limit theorem and a sample size, obviously it doesn't really matter because the sample size is big. If it's small though, you can't do this. And so you have to assume. So I give you a little something to think about there, just to make the point about the central limit theorem and the power of the central limit theorem. And the less assumptions that you make, the better, because it's just adding errors on top of errors if you make a bunch of assumptions. You should never do that, right? Make no assumptions. It's not good. There's a rule, not a rule, but it's what is it called? The Four Agreements. It's a good book.
What it does is reduce the chances of error.
Yeah.
You are assuming, but it's just reducing the
Yeah.
Yeah.
Exactly. All right. What else? That's it, right? I did 3 and 4. Any more? You guys are going to be okay with the control charts? It's just a matter of Mhm.
So Professor, maybe it's a little bit go back, but I have some questions with the page 37.
Yeah.
And yeah,
Same
that
sort
one.
of thing, right? Yeah. Same idea here. Except that we know we cannot assume normality here because the variable is a count variable. And we don't know anything about it to be able to assume it's normal. It can't be normal because a normal distribution is continuous and a count variable is discrete. So how many people in a car? A study of rush hour traffic in San Francisco counts the number of people in each car entering a freeway at an interchange. Suppose that this count has a mean of 1.5 and a standard deviation of 0.75 in the population of all cars that enter in at this interchange during rush hour. Could the exact distribution of the count be normal? And you say no, because it's discrete.
So during the exam, writing no because it is green, it's okay, or I
Yeah.
need to make some of calculations.
For that one, you don't need to make calculations.
Right.
Yeah, just a comment. And then also, it's not continuous, and also because you don't have any other information. Remember, the binomial distribution can be approximately normal, but it's not going to be exactly normal. So if we said, okay, the binomial isn't even, this wouldn't even apply because the binomial is when you're looking for something and you're counting the number of things you see. This variable isn't even binomial, so we can't even use that from what we have, right? So we're counting, we're just simply counting. It's not like we're looking as we count for something. So it's not a binomial either. So no, because it's discrete, not continuous, and no other info is provided to do anything else with it. What did I say in the answer? Let's see. No, since count, let's do whole number values. Yeah. But that's what I'm getting at. That is discrete, not continuous. Should I continue?
Yes.
Okay. Traffic engineers estimate that the capacity of the interchange is 700 cars per hour. According to the central limit theory, what is the approximate distribution of the mean number of persons, X bar, in 700 randomly selected cars? Okay, so what are we doing? We begin with X is the count. So I'm using X as the count of people in the car. So X is the count of people in a car at the interchange. So X is 1.5 on average with a standard deviation of 0.75. Hopefully everybody knows I'm putting mean and standard deviation there like that. But it's not necessarily normal. There's no pattern. We don't know anything about it. I just calculate the average. Or no, I'm given, don't get confused. But even though we're doing this study here, we are given, when you're told you're given this, these are population parameters, okay? So be clear. This is the weird part about what we're doing before we get to inference, is that we assume we have the God-given information. And then we take a sample of 700, and that's large enough to use the central limit theorem to say that the average number of people in 700 cars is approximately normal with the same mean, but a standard deviation that is smaller by a factor dividing by square root of 700. What number does that give you? Oh, there's some questions in the chat here. Go do them.
0.028.
Everybody agree?
Yes.
Good. And then, so this is because of what's called the central limit theorem. I didn't have to know anything about the shape of the distribution, just the mean and standard deviation to compute this result. And now I'm going to,
Professor, sorry, I have a question. In your videos, you said that we should have 4 decimal digits for
oh,
the
okay.
exercises.
Yeah, like give me one more. Yeah, you should keep 4.
It's 3.
3.
Yeah, keep 4. So you can follow along with me. And then, thank you. What is the probability that 700 cars will carry more than 1,075 people? Okay, so this is, everything so far is probably clear. This is the one might be a little confusing. And I tell you I hint to you, this is asking you about all the cars, but we only have information on the average in each car, in other words. So this would be defined as So if it helps you, write it always out, like spell it out for yourself. This is the average count of people per car out of 700 cars. So that's what we have information on. But this question is asking you for the total of all the cars. I can only find out the answer for per car. But I'll sort it out later. So I'm gonna solve for solve for 1,075 people in total. What would be the average? That's the one step I have to take to be able to apply this formula or this result. I have to convert 1,075 to
$1.54.
that's what you're going to look for. Otherwise, you can't solve this. Okay, because the only information you have is about the average number of people per car. Well, now we can answer the question. The average number of people per car is greater than 1.54. In other words, more than 1,075 people and 700 cars. It means the same thing. So I standardize
Professor, it would be 1.41.
Thank you.
But we have to go look at the table. Or no?
Yes, mm-hmm.
Okay.
Yeah, so then you round to 2 decimals because you need the table. You can go in the table, you can go in Excel. So either you can go to the left and 1 minus, or you can look at 1.41 negative.
It's 0.0793.
Yeah, 0.097.
Great.
Oops,
Yeah, I didn't.
what just happened here? Anyway, you see it. Right, because it's and when you make a picture, you can also have a verification that that makes sense. That's small. It's not more than 50%. It's smaller. Yeah, 7.93%. That's right. So you can write it as 0.00793 or 7.93%. All right, is that okay? Aren't any more in this unit? Let me see. There was any other question. There was one I saw was the homework. Homework 22. And Catalina asked if x greater than 40 is close to 1. That was from the other problem. Let me see what happened there. Yes. Oh, I never finished answering this question. Did I? Oh, did? Oh, I did. D. But you asked 40, is 40 greater than 1? Or B? What did I do here? Did I not answer B? What happened? Oh, it's a different question. Then it was this one. Then it was this one. Yeah, I just talked about the assumptions, but you should get the same answer. And 40 is greater than 1 because, not 40, but x bar greater than 40 becomes z greater than -10. I'm sorry, I'm just responding to something I saw in the chat. And so -10 is way back here. So that's the whole distribution, right? If the normal is over here, -10 is over here. That means it's all the whole distribution. So yeah, it's 1. All right, so I'm going to look at homework 22. Okay, let's see if I can get the homework. SDS 22. Uh-huh. Okay, so question 22 is like the one that we just did, where you need to use the average. You have to convert the question into an average to be able to answer. Let me see if I can bring that on my platform here.
I think I got it now, Professor. I will try it. I was confused about the part of the average.
Okay, for 22?
Yes,
Okay,
thank
good.
you.
Okay, good. Yeah, because they're similar. Yeah, good. All right, so then, all right, so we're going to move then, unless anyone has any other questions, I'm gonna do an introduction of inference that's gonna look pretty much like the videos, but I guess it can't hurt to see a review. So I'm gonna go back to my formula sheet. I'll start with a problem. So I'm going to ask, there's a lot of notes in the inference unit. There's a lot of notes, a lot of pages, but really it's just a bunch of exercises. Okay, it's several exercises, and do your best to get through it for next week. So we can just start solving different problems rather than the same ones. So I'm going to do my best. I have an hour. I'm going to introduce you to inference and the 3 or 4 types of problems you're going to see, and the 3 types of contexts you're going to see them. Okay, so I'm going to begin with this type of a problem. So it's interesting because my notes are very relevant now. We've all been through a hyper focus on vaccines, so I have a lot of examples with vaccines. And I made these notes years ago. But maybe they'll have more impact. In a study with a new vaccine involving 53 lung cancer patients, 29 survived 5 years after surgery. The approximate 98% confidence interval for the true proportion of patients surviving 5 years after surgery with the new vaccine has these endpoints. Okay, so if you've never taken stats before, it's fine. I'm going to explain all of this. You may have heard some of this terminology before, and in fact, let's look at what you do know, right? And let's put it in the framing. Let's frame it as we have previously. So let's read this again. In a study with a new vaccine involving 53 lung cancer patients, what symbol would you give for the 53?
N.
Excellent. So it's a sample, right? So this is 53, so that's not so new. 29 survived. What symbol would you give that?
Successes.
Excellent. Success, right? In the very true sense of the word success. So this would be, what letter should I make it? So this is success. Which variable counts successes? What symbol have I been using? Well, what variable? What kind of variable counts successes?
X.
So
X.
X, right?
X.
Right, X, very good. So X is 29, that's counting the successes. So I use X. And it's funny, yes, I use X for normal and X for other things, but in particular, I define my X as the number of successes, right? When I use it as a binomial. Okay, so we have an X, we have an N, and now I want to find something about the true proportion. What is the symbol that I will use for the true proportion?
P.
Excellent. So P is the true proportion. And so now, once we're in inference, once we're in the last module, module 9, we no longer have the privilege or the honor of having the God-given information about the parameters. We only try or attempt to estimate them. Okay, so now we're going to talk about P like it's the thing that we want. We don't have it, but we're going to get a sample to estimate it. What's the best estimate of P that we can get from this sample?
Hat.
And what is P hat? P hat is X divided by N. So we'd seen all this before, right? If you guys are caught up and you did the binomial and the SDS, you would have seen this. And I would be giving you, I usually gave you P and N, but now I'm going to give you X and N, and you're going to have a sample result. So with that, what is the sample proportion? 29 and 53. What is the proportion, the sample proportion of people who survived?
0.5472 or 54.72%.
Yeah, exactly. So 54.72% of people survived. Now, all of these have that answer. So it's not helping us differentiate which is the final answer. So it turns out, because of the randomness, remembering back what we talked about, that P hat has a distribution. It's approximately normal with a mean. Do you remember, or look at your formula sheet? What was the mean of P hat? Go back to your formula sheet and see.
The same as P.
Yeah, so the on average, the mean is P, and what's the standard deviation?
It is
So if we knew P and if we knew P, then we could take, okay, so this is the distribution of P hat, right? Because what we have here is just one sample, but that sample comes from a distribution of p hats. It's normally distributed. If I made a histogram of all the possible samples that I could calculate p hat from, it would have a normal distribution and it will be centered at p and would have a standard deviation of p1 minus p over n. So the one that we got actually is just one of the whole distribution. So what we're going to do is we are going to make an interval around it. We're not going to just present one value. We're going to create an interval around it. And the way we're going to do it is kind of like cheating, but statisticians, they proved it using the theory that we've derived. They proved that this is, this has a low chance of error, right? And we'll talk about what that means. But what they're going to do is, because you don't have p, they're going to substitute in the next best thing. What's the next best thing to p? It's p hat. So they're going to put, this will be like their mean, and then this will be like their standard deviation. And then they're going to make an interval where they're going to say, okay, so I'm going to take the mean plus or minus, like I can do 2 standard deviations from the mean, right? So that's just the kind of interval we've talked about before, 2 standard deviations from the mean. Now let's put in what we have. We have p hat plus or minus like 2. I'm just using the number 2 for now, because this will catch 95 because it's normal, approximately normal, catch a lot of the values around p hat, 95% of them. And the standard deviation will be this p hat 1 minus p hat over n. Okay, so the only thing I'm going to add to this is I'm going to be more specific about if it's 2 or 3 or 4. And I'm going to say I want not 95% of the observations or of the outcomes. I want 98%. How will I get 98%? What should this be? Not 2, but to get 98% in the middle.
It should be 3.
Not 3. I want to be precise. So let's see.
2.5.
So let's, yeah, you're getting closer. You're getting closer. So I want 98% in the middle. It means that it's going to be 1% on each side, right? 1% here. 1% here. So what will the z be here?
Point 4960.
Otra vez.
4960.4960.
No.
46.
Okay, where are you guys looking? So it has to be, you have to look up 1% inside the table to get the z backwards.
Yep.
So
Sí.
you go. Uh-huh.
Negativo 2.33.
There you go. 0. Sorry. 2.33.
33.
Very good. And that's a negative. Okay, so it's not 2. To be precise, using the tables to be precise with 4 decimals of probability and 2 decimals of z score, this should be 2.33, right? So I want 98, not 95. I'm going to be. So I'm going to call what I've done here, this value here, we're going to give it a name. It's going to be called the critical value. okay, the critical value, and it depends on the size of the interval that I want, that we call the confidence interval. So it's going to be larger, the larger the level of confidence, and we'll talk about that as well, the larger the value, because it's going to spread out this area more and more. So,
I have a question.
uh-huh.
So I got in the table 0.01, negative 0.01.
You have to go backwards. You go inside looking for 0.01. I'm going to show. So I have to look inside here, 0.01.
So isn't it 0.4960? Or
So 0.01 is between here and here. See?
oh, okay, I got it.
You got it?
Yeah.
We haven't done this for a while, but we're gonna do it now. So go here, and it's the closest one she picked was negative 2.33 right here.
And if it were between two, then you would average the two.
Exactly. Okay, so we got negative 2.33 on this table. Now we have one, we can even get more precise, and that's using the new table I've added here, and I will explain it. It looks like the normal distribution, but it's different, slightly different. It actually depends on the sample size. Okay, so it looks like the normal, we'll talk about it. But at the very bottom, that table gives you to 3 decimal places, more precise, the confidence or the critical value for the confidence interval. So here it's 2.326. It adds one more decimal. If you rounded it to 2, it would be 2.33, but so I could actually take it from here. Now, this row shows Z star, and that's the symbol that we're going to use for critical value. It's just
Will
the
be-
number, it's just the number of standard deviations you have to be away to get 98% in this case. Question?
Yeah, are we going to use this table for all the problems?
You can use this table, you can use Excel, you can use the other table. Okay, so you're free to use whichever one. I'm just showing you where the number is coming from to have 3 decimal places out of the tables. But you might want to even use Excel to see, that precision. Okay, so let's go back and wrap this up. So what I've shown you is the first pass. If you've never seen or done anything like this before, is we have constructed an interval like we've been doing before, but we have some theory around the mean and the standard deviation. We can use a sample result and we can calculate this interval. I'm going to replace this with the one that we saw, 2.326. It's more precise. But you could have picked with that 2.33, you still could have picked the right answer, right? That last table we're going to learn about, that'll be the last thing we focus on learning, is how to use that table and when. So now you punch in the numbers, you'll see that this one is 0.547. And then let's put this in together because, you're going to make a lot of calculations like this. So it's nice to be able to get it right the first time. So this is going to be. Right,
I have a question. Does the mean plus negative 2 standard deviations is like the standard way to do these exercises? Or we
I'm
can
gonna give you a general formula. I'm gonna have a general formula. So I'm gonna change the 2 because that number is gonna change depending on the confidence level. So that's gonna be changed. So we're gonna use Z star to talk about it. So that is the standard way we're gonna make a confidence interval. Okay, so I'm relating it to what you learned before, but we've learned something since then. And we have a pattern for the mean and the standard deviation that we can exploit. So the standard deviation is 0.5472. And then this one is we got to do 1 minus 4, 5, 2, 8. And then I forgot the square root around here, didn't I? You have to have a square root there, or that won't work. And then divided by n. I didn't do it here either. Need to have the square root. Because otherwise you have the variance and you want the standard deviation. And n is 53. Don't forget that. All right, so punch that into your calculator or your computer, Excel, and make sure you get, so we're down to, we know it's either this one or this one. So it's B or E. Which one do you get? No, sorry. Yeah, B or E. So I just went through and added all my square roots in because I forgot them. Don't forget them. And that result comes out of the theory, the sampling distribution of the statistic p hat, and using the rules of mean and variance to derive them. I derive them from the rules. Okay, good, good, looking good. So I suggest that you write the number here, not 1 minus, because that leads to possible more error. Okay. So the answer is D. D? Not D. How can it be D? It's B. It's B. Because you have to remember it has to be B or E because we have to get this number, right? This is the critical value. So then this one is 0.0684. So this is the answer here. So don't forget to take the square root. Don't forget to take the square root. Be careful with your 1 minus. And you will be okay. Okay, so we can leave the answer like that. Or we can actually make an interval with the values. So that can be presented in a different way. So you can see examples like that as well. So we're using the old way of doing things. We're creating an interval that catches because of the normal or the symmetric nature. We're going to catch in this interval 98% of the possible values. So people well, actually, let's just do it. Let's make the interval. Let's actually make the interval together for the interpretation. So where can I do that? So make it into an interval with upper and lower limits. What numbers do you get? Okay, so if you don't round it, okay, I don't know if it's gonna matter, so I'll round mine. I'll put it down to 0.0684, 0.0684 to make sure I get the same numbers, times 2.326. I'm gonna store that value and I'm gonna subtract it from 0.5472. 5472 minus recall 1. This is difficult with all the decimals in it. So 0.3881. I feel like I did something wrong. Okay, let me do that again. So 2.326 times 0.0684 is 0.1590984. And I stored it in 1. And then I took 0.5472 minus recall 1. Yeah. And then I took 0.5472 plus recall 1. Okay, so between you will so it's saying that the true mean 98% confidence interval for the true mean is between survival of 39% to survival of 71%. It's quite broad actually. So if you're looking at trying this vaccine with these results, you need to know the side effects, right? To know if it's worth it. Or if these are just people who are terminally ill, they might just try it. Because look at this high chance of survival. And that's 98% confidence interval. This is not so bad. They're 34% survival. Okay, questions? You guys can get those numbers? Okay, good. So that if we can stick with 4 decimal places, I'll do my best to be consistent with that. So what have we learned? So we've learned to the formula sheet. So we're here now, row 4. So when it comes to inference is educated guessing. So we're performing inference on P, the true population proportion. And we begin with a C, what they call C% confidence interval. Which in general has this form. I call it point estimate. So that's the unbiased estimator of the parameter plus or minus what's called the critical value times the standard. So we usually call it the standard error. Now, in this case, I called this the standard deviation because it was the standard deviation in the formula, but because I put an estimate inside of the formula for the standard deviation, it has a new name. Okay, when you put an estimate inside of an estimate, that's what it is. They call it a standard error, so it has a different name. Okay, but it's like the standard deviation, but with the estimate inside. So I'm going to make this the heading here for this column because you have the same thing here. But what is this inference for? This is inference for P. Well, what's this inference for? Like these numbers all should look familiar. What are we estimating here? So P hat what is an unbiased estimator on P because in repeated samples, the the mean of P hats is P. That's what the theory showed us. So here in repeated samples, what is the mean of X bars? What did we learn up here in the third statement? And what we just did examples of. The mean of the X bars is the true mean. So that means that X bar is an unbiased estimator of the true mean. So this is inference on the true mean. And very specifically, even though I don't know, so here I don't know P, right? P is not known. So inference on P because P unknown. Here, inference is on mu, but how funny it is, we don't know mu. Mu is unknown, obviously, because we're trying to guess at it. But sigma known, which is awkward, but we're going to use the theory to develop what's more realistic is where sigma is not known. Okay. But yeah, we're going to know mu, but we're not going to know mu, sorry, but we're going to know sigma some miraculous way. But then I'm going to get to the more realistic situation. So we build this theory up, we build this foundation up, and then I start taking away some of our assumptions or some of our parameters and replace it with unknowns. And that's from there we build our theory. How could we possibly determine what that is? Well, with these certain criteria, you can find it. So in this case, as long as you know sigma, this would be the formula for the confidence interval. This is the point estimate. This is the standard deviation. In this case, it actually is a standard deviation because I didn't put an estimate in there. That's the true proportion, the true standard deviation. And this is the N. So this would actually be called standard deviation, but usually the habit is to just call it standard error in all the software and in discussions and papers, they usually call that just the standard error. But okay, so let's get back to this. So on this one, let's just say this one is inference on mu. Sigma is unknown, but also, sorry, mu is unknown, but also sigma is unknown. Not knowing sigma, the best thing to do is to replace it with S. Remember the sample standard deviation. And there's some theory around doing that. The price of which we can't use the standard normal table, we're going to use T, the thing I just showed you that we used on the bottom row for. That T distribution gets used. So that's the compensation for not having the true value. Okay, so that's also called a critical value, as are these, and these are called standard errors. And it's all based on things that you learned in the first few weeks of class where we learned about the mean plus or minus 2 standard deviations, etc. That kind of discussion for symmetric distributions. Okay, so we're going to spend more time on these later, or you're going to practice this week on those. I'm going to talk now about this column. What is this column? This column is instructing you how to find sample size. Now, this is a very practical situation, a practical tool. I guess estimation. Okay, so I want to find the right sample size in order to get an estimate of P with a certain level of confidence and a particular margin of error. So M is the new thing here. M stands for this whole thing here. This is M. M is equal to the critical value times this. This is called M, the margin of error. So it's the interval, it's like half of the interval, right? Because we do plus and minus, so it's half of the interval. It's the margin, like if you think of the marginal, it's on the one side, right, of the estimate. So what we're going to do is take this expression, and instead of isolating for M, we're going to isolate for N. And when you do that, you get this, and I'll show you how. We'll do that together. But that's where it comes from. It's nothing new, but we interpret it this time. We're, rather than having all these values and putting them in to find the confidence interval, we're going to presume we don't have a sample, right? Because this is all derived from a sample, right? We got this from a sample with the sample size, and someone told us to make a confidence interval of certain percentage. Here, we might not even have a sample yet, but we want to estimate P, and we need to know the sample size to collect that sample to estimate P. So that's a very practical problem. So let's take this, and so isolating for N means I go M over Z star and then I square both sides. Okay, let's see if you catch up with me. And now when I need to solve for N, I want to isolate for N and then say the other ones are given, then I have to cross multiply. When I cross multiply a fraction, this happens. I think I put in the formula, hold on. I have it at the front, so I'll put it at the front. I have it at the front. So this is Z star over M squared equals N. So this means that the sample size you need depends on the level of confidence. The higher the level of confidence, so the higher the level of confidence, the larger the sample size you need. lower the margin of error, so the more narrow your confidence interval, more precise your result, that would mean that so the smaller the denominator is, the higher the n is. So it means a higher sample size. And then it's multiplied by these. Let me clean this up a bit because maybe it's hard to stare at. Let me move this. And then it depends on this. So P, what is P? Now I have it as a hat because I borrowed it from the formula for confidence interval, but I don't necessarily have a sample, right? So really this should be, if you don't have a sample, so if P hat is unavailable, so first you could use the true P if it's known. Now that would be weird. Why are you trying to estimate P if you already know P? And we already said you don't know P. But if you had it, you would use that. To, if you had some previous sample, you wanted to just try and use that one from an old sample. Or if you didn't have any information at all, and you didn't trust old information, use P equals to 50%. Okay, because it's halfway. It's like, no value of the proportion is any better than the other, but we'll just go halfway and be unbiased in a way. So
That would be the best option.
if you don't have any information, you don't have an old sample, no one knows anything, that's what you do. So usually you're going to do this, but sometimes you might have some other information. Okay. So this gives you the sample size for a certain level of confidence with a certain margin of error. And so I change my formula, I change into a bunch of estrellas. So I call this the Mazda, this is my Mazda formula because this spells zoom zoom. I don't know if you remember the zoom zoom commercials for Mazda. This is Z over M squared. Like, you're going to have the formulas, but it just helps you remember to square it. Okay, because that's common that students forget. And I'm going to change this to a P star instead of a P, and say P star is I'm going to say P star equals 0.5. So let's try a problem. I'll let you copy that and we'll try a problem before we go. And I will talk a little bit about inference hypothesis testing. Do you have a class today, the other class?
No.
No.
I don't want to burn you out, but I just want to launch you into studying this. So I'm going to say a few things after we do this exercise. All right, so this is our formula. We can take it back with us, or we can just look at the formula sheet. Okay, so here it is, right? I'm just copying it. That's exactly what we got here. And you understand it comes from here, but we're using some predetermined values. So I have to give you the margin I want. I have to give you the confidence interval I want, so you can calculate the sample size. And M is the margin of error. Don't forget. That's what that is. So let's go back to the exercise and see. I left some space to calculate it. So I presented here and then I solved it in the videos and I get that result and I have my situation. So here's my problem. So try this one before we go. Give you 5 minutes and then I'll talk like 5 or 10 minutes about the other stuff. The last column. How's it going?
I've only gotten to the critical value.
Okay, keep going, keep going. Okay, you ready? So when you start your review of the class, unless you want me to repeat all that, you can skip over the video to where I end this. But that's up to you if you want to watch it again on high speed. Remember to also use the Brave browser. Some students think I'm making money off the ads on YouTube, and I am not. I am not monetized on YouTube. They just make money off of me and us. But there's not much I can do about it because I like the platform to store things. It takes big files and it's always usually works. So that's why my stuff is there. And for the translator and okay, so yeah, use Brave browser. Okay, so let's put this together. Suppose that we wish to estimate the proportion of Canadians who actually understand the Constitution of Canada. What is the approximate number of Canadians who need to be sampled? So that 95% confidence interval. So this is going to help us get our Z star. And this is maybe the confusing part. What is the width? Okay, so the formula we're going to use is this one up here. Actually. So I want to use that. So that's going to be the n I want to find is equal to a Z star. So Z star is going to have to be for 95%. And then I need M. So M is the margin. The margin is half of the width. All right, so that's how you figure that out. So, or in other words, you know, two margins make the whole interval, the width. Not to confuse you, but sometimes they talk about the width of the interval, sometimes about the margin. So usually about the margin. So you need to know that relationship. So the margin would be, if it's 2 percentage points, then this is a 1 for n. Actually, I'll make the calculation. So this is 1/2 of 2 percentage points, or 0.01. Okay, so now we have the M. So we have the Z. Oh, we have to still do that. We have the M. Now, what's the P star? Do we have any information about P here? Is there any information about the possible true proportion? Is there any information about P? No, there's none, right? So
0.5.
yeah, just use P star as 0.5. There's nothing else there to go on. So let's get the Z star of 95, and we can do that using the last table easily, rather than going into the Z table. Now notice we only have a few here. There's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's only 12. So if you cannot get it here, you have to do it the long way. You have to make the picture and think about what's outside and all of that. So here it's 1.96. If I was to do it using the table, which you should be able to do, remembering that we want 95. Let's see. Let's go here. I want 95% in the middle. And we know that's about 2. But to be precise, what is it to be precise? So this would be 95. This would have to be 2.5 or 0.02500. Right? And this would be 2.5 over here. So what would negative Z be? So look for 0.0205. It's like between these two, right? Oh, sorry, no. 0.025. 0.025 is here. Oh, we found it perfectly. Look at it. Negative 1.9 You see, it's perfect. Okay, so that's how you would do it with the table, with the Z table, but you can do it here with the T table at the bottom, because the larger the sample size, the closer the T distribution gets to the standard normal or Z distribution. So that's why we have this row here. So this is 1.96. So I've done it both ways to teach you. So 1.96 is my C. And now I can put it all in the formula. Don't forget to square. And if you use 0.5, both of those numbers, that's the largest it can be, right? Because it's 0.5 and 0.5. 0.25.
So, I mean, if it's 0.5, it'll always be 1.96.
No, the 1.96 comes from this part.
Ah.
The 0.5 comes from, there's no information about P. So I have to use that one. And then I put it together on my calculator. Don't forget to square. So there's many places you could go wrong here, right? I just made that more complicated problem first. 0.96 divided by 0.01 squared times 0.5 squared. And you get 9604. So which is the best answer? Okay, it looks like E is the right answer. Now I have to tell you something in particular before I go. And I'll say, what if D was if you had to choose between those two, which one would be the right answer?
E.
Why would E be the right answer?
It's closer.
Okay, let me change it because I knew that was going to happen. Okay, I'm going to change it. Which one should you pick?
You choose E.
Okay, why do you choose E?
Because you have to round up.
Very good. So she was ahead. So you have to round up. You have to choose E because what we're trying to do is get precision within 2 percentage points. The higher, because of the formula, the way it is. Oh, I erased that. Because of the formula, the way it is, the higher, okay, let's do it backwards. The lower, the smaller the margin of error. So more precision requires a higher sample size. So if you want to retain the margin of error, you can't choose exactly 9604 and you have to choose between these, you have to round up to make sure that, so this is going to be higher to make sure you're like M or smaller in your margin, okay? To keep it as M. You want to make the margin small, so you have to round up. And that's all I'm going to say about that. And I have a lot of examples where I talk about that, and it's all very practical, and it all relates back to this formula and how these variables affect N. Now, as a statistician or as a researcher or as a student assistant, whatever the case is, you can control the size of your confidence interval. You can pick what kind of confidence interval you want. You can decide what the margin of error it is that you want. You can't really choose P, right? P is either given or you use 0.5. Those are not within your control. All right. Questions about this? So this says round up to maintain the margin of error or lower or less. I think that's a word. So the last thing before you go, I take extra 5 minutes, is to just talk about this for a moment. So we've done sample size estimation, we did confidence intervals, and it applies, the sample size estimation applies also here. Similarly, I can take this and isolate for N and I get this formula. And then we'll talk about why that's not there. And you can see I discussed it on the videos, but then we have this column. So this is the last column, and this is known as hypothesis testing or tests of significance. And as usual, I like you to look at something and relate it to what you've seen before. Notice, first of all, this whole row is inference on P unknown. So notice there's no P, there's just P hat, there's a P star, and there's no P here either. There's P hat, P0, and that's it. There's no P. So what do we see and recognize here? We recognize this looks like the standard deviation, but using P0. And then we see this whole thing happening here. So what is this? And then this says Z. Why does this say Z? What is Z?
Standardizing.
This is standardizing. We're standardizing this to the standard normal. And Z is a statistic. We call this a Z statistic. What did we standardize? What we're going to do here is we're going to assume something to be true, and then we're going to look for evidence from a sample against our hypothesized value. So we're going to assume that the sample proportion is a certain number, and then we're going to use the sample result from an actual sample and test to see how different they are, to see if this is, you know, how many standard deviations they are apart, in other words. Okay, so that's what we're going to do here. And then if it's an outlier, then something is wrong. And if something is wrong, we have to remove our assumption, because that was the thing that we took a stance on our assumption. If something is wrong, if this is an outlier, if these have a standard deviation, or sorry, a standardized value that makes it an outlier, then we're going to say something strange. The strange part is that probably something's wrong with our hypothesis. We reject our hypothesis. Otherwise, we say we fail to reject. So this is where we're heading with this. And keep in mind, this is something you've done before. I just go through some steps to lay out what all this is. And I use a 5-step process to solve this. And then as you get good at it, you can kind of skip some of the steps, right? And notice it's the same here and here. You do the same sort of thing, but in different circumstances. This is all about sample proportion and the other two about the sample mean. All right, so I'm going to send you off to begin your review or continue your review of inference. And next week we will solve problems and I will focus mostly on the t-distribution, but if you can get ahead, keep working ahead so you can finish the videos on your own. We have a lot of problems to do. Collect your problems, your exercises, and we'll discuss them next week. The assignment for module 8 is still up. It should be up till Tuesday. And then I'll put something up for inference, and I'll put an extra assignment as well after this week. I mean, extra for people who missed an assignment and they want to replace an assignment.
That's count for all the assignments?
Yeah, because I'm not going to grade, I'm not going to use all the grades. I'm going to use most of them, but some people missed several assignments, so I'll give them an extra chance. They don't have to do it. That won't be counted.
Okay.
Yeah, you don't have to do it. It can just replace a low score, or it's not a requirement. So there'll be one this week, and then there'll be an optional one the next week.
Are you talking about the next?
Yes.
How many are they?
I don't know. I don't remember. I think we're on 6. Let me see what I put on the platform because I have it there.
I saw 5.
You told that we can miss 1 or 2, right?
Yeah, you can miss 1 or 2. I have 5. So then, yeah, so that will be due on Tuesday. And then I will put 6 up. And then that will be due in a week. And then I'll put 7 up. And 7 you don't have to do. So it will be out of, I can put it out of 5. So if you've done all
And how
5
many
and you're
are-
happy, if you're happy with the 5, you don't have to do any more. And the next 2 you don't have to do.
But do we have how many attempts to do the exercises?
It should be unlimited.
No, there's 3 attempts.
Oh, it was 3 every time? No, just this one?
No, 3 attempts at each quiz.
Really? I thought I put it unlimited.
No, actually, the last one, it's written just 1 attempt.
Okay, I can fix that.
Thank you.
Yeah.
Professor, I have 2 quick questions.
I think I put 3 attempts, just 1 second, because once you've done it 3 times, it's not many options. You should know the answer. Right?
The one for Tuesday, in my computer, it appears just 1 attempt. I still didn't start, but I just like, why is it written 1 attempt? Generally, it's like we have until we get 100.
Yeah, because I used an old assignment and I edited it, and I didn't edit that. That's why. Because I edited an old assignment and it had 1 attempt. But I can change
It's
that.
gonna be just 1 attempt.
I'm gonna check. I'm verifying.
Thank you.
Uh-huh. So
Do we have classes on the 21st and 28th, or just the 21st and the 4th?
one moment. Let me fix this. So 3.
Okay.
You guys are fine with the 3. Okay. All right. So your question was, do we have a class on the 21 and the 28 and the 4? Why, is there something happening on the 21, 28? I would like to have class on the 21, the 28th, and the 4th.
Yeah.
Okay.
Elizabeth, you are in mute.
Yes. Elizabeth,
Oh, okay. No, it's just because I thought that there was like the 21st and after the 4th, because it was like 3 each classes, but maybe it's 2 each classes. It's not there in the modules.
Oh,
and
yeah, because I went by 2. Because that just
Oh,
shows you when you need to
yeah.
complete. Yeah.
Okay.
Yeah. So you have, that's the idea. You should be finished by the 4. And then we'll have a class on the 4 just to answer questions and calm you
like
down
a
because
review,
you're stressed. And, huh?
like a review, like we can.
Yeah. You can bring questions. I'll give you questions. And we'll work together, just like we did last time.
So it's not that in the last class there will be material that's going to be already in the
No.
test that we have to start on Saturday. Okay.
Yeah, no,
All
no,
right.
no. By
Okay.
next week, I mean, I should finish everything by next week. I mean, you should finish everything. I put 11.4, if you're pushing it, but you should have a complete review of everything before the test, sure. But I know it's not everybody can do that. So they'll still be studying while they're writing their test. I know what's happening. So keep me posted then on any questions you have, or if I can help move you along without delay, you can contact me, okay? Or we can meet. We can have a virtual meeting if you like. So keep me informed of your progress. I think you have more than enough exercises to work with, so I don't want to give you any more work. Do you agree?
Yes.
Yes.
I don't want to give you any more new stuff
That's-
because that's just,
So for the last class, we should team with the mock exam, right?
so for the last
have-
class, yeah, for the last class, you should have done the mock. That's right. So you should have done the mock, and I have the solutions already there, and we can talk about it.
Okay.
And remember, your exam is going to be like the mock, same sort of questions, same format, same distribution.
Professor, will ANOVA come in the exam?
No,
Because-
I never
okay.
get to ANOVA. I put it there, but I never get to ANOVA.
Okay, so module 9 is the last one.
Yeah.
Okay, and another really quick question. When we're using the T table, how big does the N have to be in order to use the C star? Is there like a specific number like for the,
After 1,000,
okay,
or if it says large, you assume that's larger than 1,000. Yeah,
okay, thank you.
Yeah. Good question. Any other questions? You guys can text me or email me or meet with me. But you can see everything is coming together now. Everything we learned that unites in the last module. We even go back to talking about match pairs. Remember match pairs from unit module 2, match pairs comes up. ¿Estamos? Everybody's ready? Okay, so have a great weekend.
Thank
too,
you.
get well soon.
Thank you.
Thank you.
Bye-bye.
Get
Have a
well.
great weekend.
Bye.
Bye.
Thank you. Likewise.